Yeah, so this is about some new advances in the learning to search paradigm for structure prediction. This is joint work with Kai Wei, who's finishing at UIUC, Alec and John, who are at MSR, and Hal, who's visiting MSR but at University of Maryland. And I'm at CMU, or finishing at CMU. Okay, so the goal of this talk is to solve this challenging problem, or to provide a reasonable solution to it. And I'm going to call this problem the structured contextual bandit. And I'll explain the problem through an example. This is the web page layout task. So the goal is a user comes to your website, you see their browsing history and maybe their search query, and you have to show them a web page, and you get to make tons of decisions about what the web page looks like. So maybe you get to set what the menu looks like and where it is. Maybe you get to set the font sizes and the colors. You get to set the position of all the elements and the content on all the elements. And so you build this web page, you show it to the user, and then you measure something like whether the user likes the web page or not. So this is a learning problem. We'd like to learn how to serve web pages to users based on their their browsing history and some features that we obtain. And I just want to point out that this is a hard problem for two reasons. The first reason is that we show the user one web page and we just measure the performance of that web page. So there's like one loss that we get to measure. And the second reason is that the decision space is quite complicated. We have to make all these decisions about different elements of the web page. And at the end, we just get to measure that one number. So yeah, the loss of just a single structured label can be observed. And you can view this as like a structured prediction type problem or a joint prediction problem. Okay, so if you think about it a little bit, you can notice that this looks kind of like a search problem. So we start with our example on the left, which is the user's information and maybe a search query. And then you make one decision, which is what font do I use? Having made that decision, you have another decision to make, which is maybe where do I put the menu, and so on until you make all these decisions, and then you arrive at a web page layout, which is what you show the user. And if you sort of enumerate all the possible paths on this, you'll get a big search space. And I'm going to call this a search space, and I'm going to denote the circles by the states or the decision points, and the arrows by actions. So this is the first step in this reduction. You convert the structured contextual bandit problem into a search problem. You define these feature maps on every search state or every decision point, and your goal will be to learn a mapping from these feature vectors to actions. And if you have such a mapping, you can apply this throughout the search space, and that gives you a policy for doing web page layout. And again, we'd like to learn a policy that has good performance. It shows web pages that users like. Okay, so now if you think about it, this is starting to look a lot like reinforcement learning. And we know that reinforcement learning is pretty hard. And so we don't really want to get into that situation. But we might have something to help us, which might be like, when we're trying to do this, we might have a reference policy or some existing solution to the web page layout problem. And we might be able to use that to sort of guide our search. So we're going to assume that we have a reference policy, which is some way to navigate the search space to produce a web page layout. And this might be like the existing approach that your website is using to serve web pages. And we're going to use this to help us navigate and learn a policy. And again, because this policy is something that we already have, we'd like to do better than that. So I hope some of you went to John and Hal's tutorial about learning to search. Maybe this is starting to seem familiar. I just want to highlight some of the subtle differences. So learning to search is a technique for doing structure prediction where you have examples and labels. It's slightly different from the contextual bandit setting where you don't really have labels. But you do convert the structure prediction problem into a search space with states, actions, and features, just as we were going to do here. One difference is in the type of feedback that you have. So in learning to search, we have like a full label, or we can evaluate the loss of many different end states. In the structure contextual bandit, you can just evaluate one single loss. And the fact that we can evaluate many losses in the learning to search problem means that we can often compute very good references. So the reference policy in learning to search is usually thought of as being optimal. It always takes you to the end state with lowest loss given where you are. In our structured contextual bandit setting, we're going to think of the reference policy as like an existing solution to this problem. And so we might not think of it as being very good. Another difference is when is the reference available. So in the learning to search setting, the reference is looking at the true labels. And so it's really only available at training time. Whereas in the contextual bandit setting, the reference is an existing solution. And so it's available at training and test time. And this is an important distinction because in learning to search, typically the goal is to imitate the reference because you can't run the reference at test time. And if you can imitate it without looking at the label, that's great. In structured contextual bandit, you need to improve on the reference. You can run the reference at test time. And so if you are just imitating it, it doesn't really matter. Okay, so this is kind of one of the big distinctions. We'd like to improve on the reference. And just to sort of put some math down, Learning to search algorithms typically give a guarantee of this form. The loss of the thing that you learn, or the risk of the thing that you learn, is competitive with the risk of the reference. And if the reference is not so good or available at test time, this sort of guarantee is maybe not so interesting to us. So this is the goal. We'd like to do learning to search with a potentially suboptimal reference. And remember that when we have such a reference, it's really important that we can do something that improves on the reference. And we'd like to do this in the partial feedback setting. So let me point out that this issue about suboptimal references can arise even in the full information setting, and that's going to be what I focus on for the majority of the talk. And for the end of the talk, I'll get back to the partial feedback case. OK, so when we have a suboptimal reference, I guess it's important to figure out what can we hope for. So what do we want? So maybe one thing is, since we don't really know how good the reference is, we should be competitive with it. If it's good, we would like to leverage the fact that it's good and do well, right? So we'd like to do well if the reference is good. If the reference is not so good, maybe we can hope for something like local optimality. And this is a definition that we introduce. It's a measure of local optimality. And this is the best way to describe it is through a picture. So here I'm describing all the green arrows are a policy that you learn, maybe like the policy you output at the end of your learning process. And so it prescribes an action for every state. And if you just change one edge, so here I'm changing this one green edge to a red edge, you obtain a new policy, which is just a one-step deviation from yours. And this policy may achieve some different loss. And if you're locally optimal, we'll say that your losses are better than or competitive with the losses of all your one-step deviations. All these policies that just differ from you on one edge. So this is the notion of local optimality, and we'd like to have these two guarantees. We'd like to be globally optimal if the reference is good. We'd like to be locally optimal otherwise. And so we're going to give an algorithm that achieves these two properties. So this is how the algorithm goes. This is also how many learning to search algorithms go. You have this search space, and you take some policy that you use to make a few decisions. This I'll call the roll-in policy. So I take this policy and I use it to make maybe two decisions, and I arrive at some state R here. Then I consider all the actions that are available at this state. So there's 3. I'll call these the one-step deviations. For each one of these, you apply some new policy called a rollout policy to arrive at an end state, and you pick up some loss there. And so now I have these 3 losses. I do this for each one, and I have these 3 losses. And what this is doing is solving the credit assignment problem. I can attribute this loss to the choice I made at that roll-in state. So what I'll do is I'll take those 3 losses, form a loss vector, take my feature vector for the state R, and feed that to a cost-sensitive classifier. And that classifier will sort of learn how to make the right decisions at the state R. And that cost-sensitive classifier basically spits out a policy. It prescribes how to take actions everywhere. And what I'll do is I'll use the output of that cost-sensitive classifier as my policy going forward. OK, so there's basically 2 decisions that you can make when you design a learning to search algorithm. And one is what is the roll-in policy, and the other is what is the roll-out policy. And the roll-in policy is important because it affects the state distribution that you train your cost-sensitive classifier on. So if you pick the wrong roll-in policy, you can have a distribution mismatch issue, which might hurt you at test time. And the rollout policy affects the way you score actions. And if you pick the wrong rollout policy, maybe you're not scoring actions correctly, and so you learn the wrong thing. OK, so yeah, roll-in affects what states we train on. Rollout affects how we score actions. So one question is, what are the right roll-in and rollout policies, specifically in the context of you might not have a good reference policy. And so this is the first, that did not show up well. So this is the first contribution of the paper. We study the effect of roll-in and rollout policies when you might have a suboptimal reference. And I'm going to show 2 choices for roll-in and 3 choices for rollout. For roll-in, we'll use the reference, which again might not be good, and the learned policy, whatever you've learned so far. For the rollout, I'll use the reference, the learned policy, or like a half-and-half type mixture. OK, so the first bad case is when you roll in with the reference policy. And basically what happens here is the state distribution that you train your cost-sensitive classifier on are the states that the reference visits. And it's not necessarily the case that the learned policy will visit those states. So the fact that your classifier was good on the states that you saw does not imply that it will be good going forward. And specifically what this means is that you'll be inconsistent. If your classifier, you can prove that you can have a classifier with 0 cost-sensitive regret, but this does not translate to low structured regret. So you cannot have a good regret transform here. So this is bad, and so you don't really want to roll in with the reference. OK, the other bad case is rolling in with the learned policy and rolling out with the reference policy. This case, you can actually be consistent, meaning your regret to the reference can be controlled, but you can fail to meet this local optimality property. And the reason is that you're evaluating your one-step deviations by rolling out with a reference, and this is not the right evaluation. When you compare with them in your regret bounds, you're comparing with rolling out with the learn policy, and so you might fail to assess those comparisons well, and you might fail to recognize that a one-step deviation from you is actually good. So you can fail to have this local optimality property. The last bad case is when you roll in and out with the learn policy, and this is just completely ignoring the existence of the reference altogether. And in particular, you won't have good regret to the reference, but this is also just reinforcement learning, so we don't really want to do that. And the good case is the last one on the slide, is when you roll in with learned and you roll out with this mixture. 50% of the time you roll out with the reference, and 50% of the time you roll out with the learn policy. And this is our algorithm, which we call LOLS, for locally optimal learning to search. And we can prove that it minimizes a combination of regret to the reference and regret to its one-step deviations. So I'm just going to flash that theorem up again, but it's really nice to look at what the right-hand side of this regret bound is. I'm not going to show you the left-hand side. It's something that's kind of small. But there's two terms here. One is your performance compared to the reference. One is your performance compared to your one-step deviations. And I just kind of want to stare at this and talk about what are the consequences here at a qualitative level. So the first thing is, this term is always non-negative, so the way we define the one-step deviations is this term, it just has to be positive, and therefore you're always competitive with the reference. This term must be small, right? The other case is maybe the reference could be really good, in which case this term will always be non-negative. If the reference is optimal, even if it's not something you could achieve, but it's optimal, this term will always be positive, and therefore this term must be small, so you have to be locally optimal. In the last case, you have to think about it a little bit more, but maybe the reference is suboptimal. This term could be big, which means you're far from local optimality. But if this term is big, this term must be negative. So if you're far from local optimality in this case, you must have improved significantly on the reference. On the other hand, the other option is this thing is small, in which case you're locally optimal. So the qualitative takeaway is if the reference is good, you're competitive with the reference and you're locally optimal. If the reference is bad, you're either locally optimal or you're much better than the reference. So this is sort of achieving the goals that we wanted. And maybe you might want to ask, maybe can we be locally optimal all the time? And we actually show that this is hard without further assumptions. So you can generate a search space where you need to look at exponentially many cost-sensitive classification examples to reach a local optimum. And so maybe the result that we showed about LOLS is about as good as you can get without further assumptions. So this is all I wanted to say on the theory front about the full information setting. Let me just present one experimental result. So this is a dependency parsing task. This is data from the Penn Treebank Wall Street Journal corpus using the standard train test split. The numbers here are the unlabeled attachment score, for which higher is better. And I'm just going to look at different roll-in, roll-out strategies and different reference policies. So remember, LOLS is this one highlighted in green, which hopefully you can see. And I'm going to bold what's the best one in every. Okay. Okay, so the first case is when the reference is optimal. This is the non-deterministic oracle of Goldberg and Nivre. And here, rolling in with learned and rolling out with reference is actually the best. But LOLS is pretty close, and everything else is substantially worse. The second one is when the reference is suboptimal. This is sort of the obvious reference, which is if the true label is available below me, go towards it, otherwise pick arbitrarily. And this is actually the usual, this is the reference that was used for this problem until the Goldberg-Nivre 2013 paper. It just kind of shows that sometimes it is easy to construct bad references, but it's really hard to construct good ones. And in this case, rolling out with the reference, the one that was doing well before, is doing much, much worse. And LOLS is only doing slightly worse. So LOLS is actually the best here, and that's kind of good. And the last case is when the reference is just straight up bad. This is a reference that just picks actions arbitrarily. And here LOLS is, again, the best. So the takeaway, I think, from the experiment is that LOLS is always a pretty good approach, even if your reference is suboptimal or bad. So let me return to the structured contextual bandit setting. I'll just remind you what's going on here. We again have to make this complex decision, but at the end of the day, we only get to observe the loss of a single structured label. And remember, the reference policy, we should not think of it as being optimal here. It's some other thing that some engineer built, and we're just trying to compete with it or do better. So here, what we're going to do is we're going to just run a randomized variant of the LOLS algorithm. And this is how it goes. Upon receiving an example, with probably 1 minus epsilon, we exploit. We just follow the policy that we have. So we take the learn policy all the way to the end, and we pick up some loss, and that's that. With probability epsilon, we're going to perform a randomized Lowell's update. So what we do is we pick a decision point, 1 to t. If the depth of this tree will be t, and we pick a decision point 1 to t, we roll into to that point with the learn policy. So here I picked the decision point was the second one, and we rolled in 1 step. Then we flip a coin, and we pick an action from here uniformly at random. And then we roll out using the mixture of learned and ref. And then we pick up some loss. So that's the web page that we play. And then we use that to form an importance-weighted reward vector for loss vector for these two actions. And we feed that importance-weighted vector plus the feature for the state R to the cost-sensitive classifier. And this gives us a new policy. So this is the algorithm. And it's very similar to Lowell's. Again, you can show that the same quantity, the regret to reference and deviations, is still bounded. The variance of your importance weighting shows up, but it's not essentially any different. And yeah, that's actually about all I wanted to say. Let me just highlight our contributions. So first, we sort of describe what might be a good objective in this problem where you have a reference that might not be so good. And in particular, we give a definition of local optimality, which is this one-step deviations. And we like to be competitive with those. Then we give an algorithm that can be competitive with those. And this algorithm can work even when a reference is poor. So yeah, it can compete with references and one-step deviations. And finally, we show that this algorithm can work in the partial information setting with an epsilon greedy style algorithm. Let me just close by saying that this algorithm is available as part of the Vopel-Wabbit machine learning system. And that's it. Thanks.